What happens when the largest rocket ever built by humanity suffers a serious malfunction mid-flight, but still manages to hit most of its targets? On Starship's 12th flight, the booster was lost before reaching the water's surface. One engine shut down during the ascent phase, and yet this mission may turn out to be one of the most significant engineering achievements SpaceX has ever recorded. How is that possible? The answer reveals a lot about how space engineering actually works and about what SpaceX is building for the future. Just before launch, the tension was already enormous. The previous day's delay had frustrated everyone, and as the countdown continued, there was a mix of excitement and skepticism in the air. But this time, something felt different from the very start. No long holds, no shifted launch windows. At 5:30 p.m. local time, right on schedule, the fueling process began. The upgraded systems at Launch Site 2 once again proved their efficiency. Large quantities of chilled methane and liquid oxygen were loaded into the vehicle at an impressive rate. The engine chill-down procedure also went off without a hitch. That matters more than it might seem. The ability to fuel quickly is absolutely critical for the high-frequency launch operations Starship will need to sustain in the future. There was one additional element that gave this mission a special symbolic weight. NASA Administrator Jared Isaacman was present at Starbase to watch the flight. His presence sent an important signal. Starship is no longer just an isolated test project. It's becoming a key piece of America's plans for space exploration. Then came the moment that made everyone hold their breath. Less than 40 seconds before launch, a hold command appeared. Viewers immediately thought back to the previous day's delay. But this time, the countdown resumed. No repeat, no rollback. No scrub. That in itself was already a win because it confirmed that SpaceX had resolved the issue with the engine ignition detection system that had caused the previous scrub, and had done so in under 24 hours on one of the most complex launch systems ever built. The launch itself was nothing short of cinematic. Water poured from the flame trench and created a curtain of mist around the vehicle. All 33 Raptor engines ignited, and Starship climbed into the sky above Starbase. No immediate damage to the launch pad, no disruptions to the launch structure. The initial ascent phase looked clean visually, but the booster and the ship were soon headed down very different paths. Booster B-19 started off well. However, roughly 1 minute and 43 seconds after launch, one of the outer engines suddenly shut down. One of the most widely discussed theories involves partial delamination of the heat shield protecting the Raptor 3 engines. SpaceX apparently decided that the new engine's higher reliability justified reducing that protection. But the environment around Super Heavy remains extremely hostile. Intense vibrations, shock waves, high temperatures, and mechanical loads that almost no system can sustain continuously. If an engine fails or becomes unstable, it can cause problems in neighboring systems. Even so, B-19 managed to reach the separation phase. The vehicle's multi-engine architecture provides enough redundancy to keep going even when one unit fails. 2 minutes and 23 seconds after launch, the booster shut down most of its engines and kept 5 running in a symmetrical configuration. What happened next is hard to make sense of. Between 2 minutes 32 seconds and 2 minutes 49 seconds, the booster's engines began firing in a highly unusual sequence. Some ignited, others cut out, others reactivated across different rings. The visual configuration looked almost nothing like anything seen in previous flights. The thrust appeared asymmetrical, one side significantly more powerful than the other. This behavior may be part of a new active spin procedure developed by SpaceX. In previous versions, the booster relied on the dynamics of the hot staging procedure to initiate rotation. With the latest update, SpaceX appears to have shifted to engine-driven rotation, more aggressive, more dynamic, and, as it turned out, significantly more difficult to execute precisely. B-19 continued its descent toward the Gulf of Mexico. Atmospheric pressure was building, airflow was visible around the engine section, and the ocean came into frame. Then came the landing sequence, or the attempt at one. About 6 minutes and 11 seconds after launch, the landing burn began, at least partially, but almost immediately something seemed off. At roughly 100 meters above the water's surface, the booster was still moving at a very high speed, one that was incompatible with any kind of controlled touchdown. The vehicle's camera feed cut out abruptly, which strongly suggests that B-19 broke apart before hitting the water. SpaceX later confirmed that the booster failed to ignite all engines as planned during the relight, executed a partial ignition that cut off earlier than intended, attempted to reactivate engines for the landing burn, but failed, resulting in a hard impact with the waters of the Gulf of Mexico. Compared to previous flights, the landing burn started with significantly less lead time. In earlier missions, ignition occurred more than 15 seconds before water contact. This time, it was only a few seconds. There simply wasn't enough time for full deceleration. Aerodynamic loads combined with extremely high speed may have broken the vehicle apart even before impact. Possible causes? Timing issues in the control commands during descent through high-pressure atmosphere, or damage caused by repeated ignition cycles during the active spin, may have reduced engine availability during the critical final phase. The investigation is ongoing. But while B-19 was dealing with those problems, ship S-39 had a completely different kind of day. 2 minutes and 27 seconds after launch, the ship successfully ignited all 6 engines. About 3 minutes in, one vacuum Raptor engine appeared to fail. Subsequent images showed a non-functioning engine with unusual smoke around it. Even so, the 5 remaining engines kept running, and the ship hit all its target acceleration numbers. SpaceX confirmed a successful completion of the boost burn and the start of the orbital phase. About 17 minutes after launch, the payload bay opened without issue. Within 2 minutes, the first payload was successfully deployed. The remaining payloads followed, including equipment for observation, communications, and testing, some of which were fitted with external cameras designed to capture footage of the main Starship vehicle in space. The result was one of the most striking moments of the mission: external shots of Starship gliding through space, captured by its own payload. The engine relight in space also appeared to go smoothly, another important milestone for future orbital operations. Re-entry began roughly 42 minutes after launch. Plasma formed around the vehicle as it endured nearly 20 minutes of extreme atmospheric heating. And S-39 handled it significantly better than previous versions. The control flaps remained functional. The heat shield showed major improvements. The intense oxidation spots that had been characteristic of earlier missions were largely absent. a clear sign of progress toward reusability. The landing burn occurred just over an hour into the flight. SpaceX intentionally fired only 2 engines, simulating a landing scenario with a failed engine. The vehicle descended toward the ocean in a relatively controlled manner, maintaining structural integrity for a few moments before tipping over and exploding on contact with the water. What looked like a catastrophe was actually a planned test, and the crowd at Starbase erupted. Overall, Flight 12 achieved successful boost, stage separation, payload deployment, the orbital phase, engine relight in space, improved heat shield performance, controlled re-entry, and the landing test simulating engine failure. Even accounting for the loss of the booster, the list of results is still impressive. And while Starship continues to evolve, NASA is also moving forward on technology directly tied to the future of space exploration: orbital refueling. SpaceX's lunar plans depend on transferring cryogenic propellant in orbit, and NASA is currently developing its own capabilities in this area. In the near future, the agency plans to launch a dedicated mission to study the behavior of liquid oxygen in microgravity and to test cryogenic fluid management technologies over the course of several months. The ultimate goal is an orbital propellant depot, a fueling station in space. This project carries major significance for the Artemis program, since both Starship and other lunar landers depend on cryogenic fuels, and long-term orbital storage remains one of the most serious unsolved engineering challenges. If this mission succeeds, orbital refueling could become a standard component of deep space travel, an idea that seemed pretty far off just a few years ago, but is now turning into a concrete reality. Starship Flight 12 wasn't perfect, but in space exploration, steady progress is worth more than the occasional flawless run. And this flight delivered a lot of progress. If you want to keep up with Starship's development and the future of space exploration in full detail, subscribe to this channel and hit the like button. Every interaction helps this content reach more people who share the same passion for space. Until next time, keep looking up.